A desire to preserve and uphold ecology, history, culture, and landscapes underlines the inception of each of the national parks in the U.S. While the Organic Act directs NPS to conserve this landscape unimpaired, the meaning of that language has always been ambiguous. Early resource managers approached conservation with the humility that nature knows best and functions best when free from human manipulation. This concept was widely prevalent in the ecological theory of the time and pervaded NPS management through the 1960s. But this idea was predicated on the fallacy that North America was once an untouched wilderness and that human systems are inherently divisible from natural systems. The consequences of this approach have often demonstrated just how much our actions or neglect can impact these natural spaces. The indigenous peoples of the Americas practiced their own forms of land stewardship and management long before the formation of the national park system. Increasingly, scientific evidence affirms that indigenous practices are an integral part of the natural history of many ecosystems, and the existence of people in North America since at least the last ice age, coupled with traditional ecological knowledge, negates the very concept of wilderness and builds a case for more active management approaches. Restoring or maintaining natural systems increasingly includes returning to traditional ecological knowledge practices, also known as TEK, and working to repair relationships with tribes that in many cases were shut out of their Aboriginal lands. In places like Acadia, Maine, pictured here, Wabanaki scientists and community members have shown that careful and periodic harvest of sweetgrass, pictured at right, is vital to stimulating the regeneration of these delicate intertidal prairies. But restoring an intertidal prairie may also require civil engineering and breaking ground with a backhoe to revitalize a water table or remove riprap that was left over from previous attempts at restoration and conservation. And it should also be noted that conservation amidst novel challenges also requires novel solutions that are going to rely on emerging technologies. Increasingly, human infrastructure, pollution in the form of microplastics, noise, and increased atmospheric CO2 saturate all aspects of both our urban and open spaces, illustrating how even the most seemingly remote landscapes are inescapable from human activities and effects. The choices land managers make, as the example of historic fire suppression or unmanaged forest density, can radically revise ecosystem function and even diversity. These ever-growing anthropogenic impacts have forced NPS to confront its traditionally reserved management approach, when letting nature take its course could mean the extinction of a species, such as sweetgrass, or the disappearance of a unique landscape feature. Active land management, from the removal of invasive species to the restoration of degraded land to assisted migration of sensitive species, is now an essential aspect of how NPS seeks to maintain healthy and resilient parklands. If we want to restore open prairie systems such as this one pictured here and bring back species such as sweetgrass, it's going to depend on people. Conservation cannot exist in a vacuum, and increasingly, these practices draw on the work of the scientific community, the expertise found in TEK practitioners, and collaboration with both public and nonprofit partners. In the 21st century, that management also includes modeling that can account for how changing climate will impact park resources, assets, and values. The continued protection of natural and cultural resources relies on stewardship that can prepare for and respond to a range of climate scenarios in park planning. Modeling climate requires broad understanding of various interacting meteorological factors. To try and understand what the future may bring, we have to first understand all the variables at play. This includes attributes such as ocean currents and convection cells that transport heat and moisture, incoming solar radiation, the Earth's orbit, gravitational forces, and even thermodynamics. It includes latitude, longitude, and the properties of the land surface itself, such as topography, vegetation cover, hydrology, and proximity to dominant features such as oceans or bays. All of these qualities we refer to as forcings. Reduced to a series of mathematical constants and equations, each climate model attempts to distill the most consequential aspect of climate. This information helps tell the story of global patterns at the smaller scale and the trends associated with larger spatial areas, such as the California Holistic Province, pictured here at right. However, more specific and local data is required to downscale these models to dimensions that will have on-the-ground practical use for our resource stewards. When modeling climate for a specific location, like a national park, climate scientists frequently rely on local information in the form of GridMet data. GridMet data offers a patchwork of about 4 kilometer resolution satellite imagery that has provided continuous surface conditions since 1979. By comparing climate models against historical GridMet trends, scientists are able to calibrate model reliability. While many parks contain meteorological stations that record daily weather patterns, weather station data typically provides a more narrow vantage that doesn't always account for the broad stroked patterns required for model scaling. So here, GridMet data is a valuable forcing that allows our climate modelers to better factor for landscape heterogeneity. In this image, now zoomed in to the California Central Coast, we can see GridMet data for soil moisture in late February 2026, highlighting the variation but also patterns that we associate with coastal proximity, elevation, and interception of incoming precipitation. NPS's Climate Change Response Program has created climate model outputs, also known as climate futures, centered on the year 2050 for all National Park Service managed sites and some national historical landmarks. Framed within the orange box is Point Reyes National Seashore. NPS's climate modelers use park centroids, or sites that are representative of the park condition, as the basis for then generating those climate futures. The National Park Service applies these climate futures in our scenario planning, but a model is not clairvoyant. It makes an estimation based on the science, data inputs, and model construction. Therefore, climate futures do not guarantee the future. In the near term, model uncertainty is affected by the limitations of what data is available and the scientific understanding of the problems we seek to model. Additionally, natural variables such as the effects of climate change or resource consumption or meteorological patterns and land use will always impact our ability to make an accurate forecast. Therefore, we think of these as futures rather than a projection or forecast of the future. We do not know how economics and politics will also play into future greenhouse gas emissions. But of course, those are truly important forcings in our modeling as carbon emissions drive climate change. It's also worth considering that drought, 99th percentile events in terms of precipitation, heat waves, and other extreme events become increasingly volatile with climate change. Just as you can imagine the specific behaviors of water in a pot on a stove become increasingly unpredictable as that pot of water approaches boiling point, as our climate warms, regional and interannual consequences become less straightforward for us to anticipate and therefore to model. Amidst this background of uncertainty, CCRP has opted to look at divergent futures. Rather than planning for a single possible climate change scenario, NPS looks to manage parks to best meet unique, yet equally probable climate change outcomes. In developing these park climate future scenarios, CCRP has tailored 20 models developed by IPCC, the Intergovernmental Panel on Climate Change, to each NPS unit. CCRP then arranged each model using two probable climate emission scenarios, denoted as RCP 4.5 and RCP 8.5. RCP, or Representative Concentration Pathway 4.5, details an intermediate carbon emission scenario, while 8.5 reflects carbon emission scenarios assuming that current rates and trends in carbon emissions are not curbed. In other words, business as usual. This scatter plot provides the hypothetical outputs of running these models for a given national park site. Evident in this plot, in all climate futures, there is a long-range temperature increase for 2050. However, both the degree of temperature increase and the moisture input are variable. This variation is captured in 4 quadrants as warm-wet, warm-dry, hot-wet, and hot-dry. While precipitation may increase with time, it's important to note that this does not imply that aridification will not increase in most models. Increased precipitation must be considered against a backdrop of increasing volatility in precipitation and volatility in seasonality. More heavy precipitation may lead to more runoff and less residence time in the soil. Or we may see years of high precipitation followed by years of intense drought that are difficult to capture in these averages. Additionally, increased precipitation may be offset as well by increased rates of evaporation, which we can expect in an increasingly hotter world. Boxed within the dashed outline are data points that represent our ensemble mean. In other words, from the cluster of multiple models, climate scientists can pull together a mean average climate future. But a side effect of working toward an ensemble mean is that extreme events and turbulence are often muted. It's these extreme climate future outliers which are of most concern for our park managers and park management. Instead of relying on ensemble means at CCRP, climate scientists use in-members to illustrate a spectrum of possible scenarios. In this figure, indicated by the blue bullseyes, two in-members represent warm wet and hot dry divergent futures, which are selected then to account for the suite of model variation. By focusing on divergent climate futures rather than averages, the national parks are better equipped to expect the unexpected, and anticipating equally likely but radically unique change in the conditions to support current park conditions, managers are able to assess which management goals will remain attainable and which management goals may need to be adapted to best meet the future needs of park resources and the public.